Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSA sheet. Topic was binary tree, pattern was BST, and today we'll see the next question, which is insert into a BST. So let's read the problem statement. It says we will be given the binary tree, okay, and we'll given the value also. And our task is ki in the BST we have to find the correct position for that value and we have to insert it as a node. Very simple question. Basically, we have to simply traverse. Obviously, you know how to traverse in BST. I hope you would have done the previous two problems, which was insert, how to create BST. Okay. So very simple. Now let's move on to the constraint part. It says the minimum number of node can be 0 also. Means there can be condition that we will not have any tree and we have to insert value into it. So can we say that if we don't have any tree, means root is null, then create a tree node type and put the root value as that value and return it. Means suppose if number of nodes are 0 and we have to insert 5, so we can say okay, here we have the tree which has only one node which is 5. Correct? And the number of nodes can go till 10 power 4. Okay, why it is important? Because if we are looking for some n square type of solution, then it will become 10 power 8. Anyhow, till 10 power 8, it won't give TLE, but beyond 10 power 8, it might give us TLE. If you don't know how I decided, then I have discussed everything in the previous video. You can definitely check it out. Now, the node value can also from minus 10 power 8 to 10 power 8. Okay, it's almost on the, edge case, where the integer can hold up to value 10 power 9. But still we don't have to worry. Why? Because we are not going to manipulate or modify with the values. Means when we have to do the summation or multiplication with that such bigger numbers, then we have to worry about okay, where to store that resultant value, in the integer format or long format. But here we are not playing with the node values. We are just looking for the value and we want to attach the correct value at the correct position, right? Okay, it's safe. So we have to insert 5, okay, as a node, okay, but currently 5 is just a value, okay, very good. So basically we have to insert 5, so we have to start from the root, correct? Remember, this value cannot match with the same 5. Why? Because here it says it is guaranteed that the new value does not exist in the original BST. Okay, so it won't happen ki root value matches with the value, okay, it will be either greater or lesser. So we have to keep moving towards left side and right side. So what will be the condition to insert? Means if it says the value cannot match, so we'll be here, we'll check, hey, root value, are you greater than this? So it will say no. It means for sure 5 will go towards left side. So we'll move our root here. Okay. By the way, if you have saw the previous video which was search in a BST, so there we have done the DFS approach also and the iterative approach also. Okay, so I hope when I'm saying ki move your root to right side means iterative approach, you are aware. If no, you can still check out the video that is of very small duration. Okay, so we'll come here. Now our root is 7. I'll check ki hey, if my root value is greater, yes. So now 5 should go towards left side. Okay, so we'll move our root to left side. Now what, at which point our root will be pointing to? Can I say null? Okay, so here, so where I have to insert 5, I got null. Is this a is this a wrong condition? Let's see. Let's say we have to insert. Let's say we have to insert 8. So for 4 we would have went here 7, and for 8 we have to go towards right side. Again it is null. Okay. Means as the question says the root value cannot match with the value, so for sure where we have to insert that number, that will be null. So can I say if my root is null, create the node with the value and return that node? Yes, means that is a condition where at root null we should not return 0 or we should not simply return, but we have to create a tree node of value this and we have to return that as a node. Okay, so always think the base case first if you are looking for the recursive approach for sure. Okay, so what I said, if my root will become null, then what is my condition? My condition is return but after making new tree node with value as it is. Very simple. But initially, so I'll be at 4 and my value is lesser than this, so we have to move towards right side. Can I say that? So basically we have to see ki if my root dot value is greater, in this case it is smaller, right? So if it is smaller than value, then for sure we have to move towards right side. So we'll go towards right side, means we'll call the same DFS function which is here DFS, where we will have root and where we will have value. So we'll call the same DFS function, and now we'll send root dot right as the main root, and we'll say share the same value. But we'll go towards right side. Okay. As of now the tree is connected. Very good. As of now the tree is connected. But when here I'll create a new 5. Remember, when I'll here create a new node which is 5, it is very important to return this to 7 in 7's dot left. Can I say that? So currently where I am 4. The value was lesser, so I'll go towards right side. Okay. So now I am in the function where root is 7 now. Again I'll check root is null. No. Is my root value which is 7 is lesser than 5? No. So I have to write the else condition, where in else condition I'll again call the same DFS function, but this time I'll call with root dot left and value. Now what will happen? Root dot left, which is 7 dot left, which is null. So I'll go here, I'll say ki hey, I have got null, so I will create a new node with value 5 and I'll return that node. Means this function will get 5 as a return node. So 7 has to save, right? Yes. So 7 has to save means 7's dot left side has to save, and 7 dot left side is nothing but, can I say, root dot left. 7 dot left means I can say 5 has been created and it needs to be saved in 7's left, means root dot left. Okay. Similarly for right also we have to do, what if we have to make 8, correct? So we'll make 8 and then we'll return, and when we'll return in 7's right we have to save, right? Yes, correct. So here we'll say root dot right. Now this question is not about just searching. Here we are inserting a single node also now. So the whole problem statement has become about the construction of tree. So whenever it's about construction, so whatever we are returning in the return statement, it is like wherever we are saving, that will be root dot right or left instead of a normal variable. Okay, because it is a construction. So okay, 5 has been saved to here. Now because now root dot left and right. Okay, now so like when we'll return to their parent, okay, 4, so obviously we would have went on root dot right, which was 7, but when we will return in root dot right, which is 4's dot right, so 4's dot right, whatever will return at 4's right, that will be get connected. And what do you think, what should get connected at 4's dot right? Because 5 though has been connected at its correct place. So do you think 4's dot right should be changed or it should be as it is? Can I say it should be as it is? So what 7 should have returned to 4's right? Can I say 7 itself? And that is nothing but, very good, root. Very simple. So what happened? We were at 4. We checked root is null. No. Value was lesser. So we went towards right side. Now for 7, what we got? No. Now its value is lesser than the exact value. So now we decided to go towards left side. So now we went towards left side. Okay. So when we went towards left side, now it was null. Because it was null, so we created a new node, and that node we have returned also. And that was 7's left call. So 7's left call will save 5 as a node now. So 5 will get saved as a 7's left child. Now after else case, it will come outside, and if you will not return the root, which is 7, to its parent, so now you know what will happen. It like by default null will get returned, and to 4's right, which was that, remember, right call, which was root's right call only na. So 4's right will save null. So hence it is very important to return the same root also. That's why I have written this extra line of code, and that's it. So the time complexity will be obviously logarithmic of n. Why? Because at every level we are only considering one node. We are not considering all number of nodes. Remember? So when we are looking for 5, like to insert 5, we decided to go either left or right. So basically at every level we are only present at one node, and then again we are deciding to go left or right. So from every level one node means number of levels, and number of levels is nothing but if n number of nodes are there, so number of levels will be log of n. I hope you know that. So hence the time complexity will be log of n, and because of this recursive call, the space complexity will also be log of n, because recursively in the stack for every node, means for every node the function call would have happened, and the recursive stack saves what? The recursive calls for number of nodes, and the number of nodes were just log of n times. So hence the space complexity will also be log of n. Although it is a fastest code, but if still interviewer asks you ki, hey, tell me the space optimized code, means you're not allowed to use that log of n space also. Can you do this in constant space? And that is only possible when you are not doing this recursive call, but instead you are starting your root and you are moving on the basis of conditions. Ki, okay, if you are looking for, okay, if you want to insert 5, go towards right side. Okay, So just move your root to root dot right. Okay, now at null left side it is null. Okay, so create and return that. That's it. Why I'm saying this fast? Because the iterative code, similar iterative code, we have already discussed in our previous problem, which was search in a binary search tree. So let's start with the iterative code here. The very first is key, what if my root is null? Key, if my root is null, then the very first condition is key return new tree node with the value val, correct? Or else we have to keep on iterating with the let's say current variable, which will start from the root only. And now as it is the iterative code, so we have to keep running in the while loop. Now the very first root is null condition we have already checked. So if we are in the while loop, for sure like the root has been checked, so for sure root is not null. So now what is our condition? Ki check the value. Ki what if the current value is, which is 5, okay? Here too we have to insert 5, okay? So let's see first case. Okay, if my current, which is value, if it is greater than current dot val, which is 5 greater than 4, yes, correct. So now our task is to move towards right side. What our task? Okay, move your current towards right side. But before moving your current towards right side, let's check ki what if my current dot right is null? Means if my current dot right is null, means that is a case where we have to set our new node, right? Why? Because you know na ki whenever we hit the null, that is a state where we have to create a new node. So if our value is less than current dot value, means for sure we have to move towards right side. But before moving, check what if my root is null. So if my current dot right is null, where we want to move, means for sure at that position don't move. There we are supposed to create the new node with the value 5, correct? So that's what we'll do. Current dot right is equal to new tree node with the value 5, okay? And now as we have created, so let's break this while loop. That's it. Now we have to put this in an else condition also, right? Else now we will do this but for left side. Why? Because obviously na this is for else, correct? So we will be moving towards left side. Now what will happen? Let's dry run. We are at 4. So in the while loop it will check the value, which is 5, is it greater than current dot value? Yes. So let's move towards the right side. Is the root right null? No, it is 7. Okay. So just simply move. Okay. Now again it will check while true. Yes. So current value is 7. Is it greater? No. So value is 5. Is it greater than 7? No. So it will go in else case. Now we are at 7, we have to move towards left side. But is 7's left is null? Yes. Okay, so in the 7 left, please create the new node and connect it. And that's it. Break. So now after coming outside the while loop, you just have to return root. So that was the reason we have made the alias to current. Because if we would have moved the root itself, how we would have tracked the main root, which is 4. So hence, instead of moving the root, we had moved the current. Okay. So that's it. As you can see, we are only returning root at the last, and in the whole while loop, we have not created any extra data structure, or we have not stored anything anywhere. Okay, we just took O of 1 time complexity to create the node and attach it. So that's why time complexity will be log of n only. Why? Because here also we are moving only on one node from every level, but the space will be optimized. So let's submit this. I hope you understood, and I hope you can do in Python and C++ as well. So that's it. Let's mark the next question as done. So I hope you would have understood, and I hope you are liking BST more than tree, because I personally like binary search tree a lot. So that's it guys. If you have any doubt, let me know in the comment section. I'll attach my social media link so that you can reach out to me if you need any kind of guidance. And let's meet in another video with some more interesting questions, topics and patterns. So then keep learning, take care of yourself and your family.